We were discussing using the binomial theorem to evaluate two-state systems. And when we do that, one of the great things to follow up with is, can we find a mean value in or an average value in an outcome? And means, of course, are pretty familiar to most people. For example, if I give a test to 30 people and I add up all of the test scores and divide by 30, that will give me the average value of the test. And the way we describe the mean in this case is not all that different from that. Let's start with, let's say we have a variable u, and let's say it can assume any of m discrete values. So I have this variable, whatever it is, it can assume, so I can go u1, u2, all the way up to un, different values. And so the probabilities, let's say that we will get this particular value u1 for u, and we'll write that as p of u1, and p of u2 will tell me how many times u2 will occur, and then all the way up to how many times um would occur. We would define the mean of that, u with a bar over it, as just the sum of the value u1 times the probability of getting u1 plus u2 times the probability of getting u2 plus all the way up to u sub m times the probability of getting value m. And I would divide that by the total number I should say by the total probability of the system, which of course is going to be equal to 1. And so I can write this in shorthand term, sum I equals 1 to m, p of u of I, u of I, divided by sum I equals 1 to m, p u of I. And as I say, normalized probability distribution will always be equal to 1 down in the denominator. So that's a nice way to express the mean value. We can take this a step further. Suppose f of u is some function of u. I can express the mean of that function, bar over it, as the probability of obtaining u, f of u, divided by, again, the sum of the probabilities, which again is going to be equal to 1. When this happens, we say that the probability distribution is normalized. If you remember back to some of your examples in modern physics, when you're looking at the particle in the box, the particle has to be located somewhere in the box, and so we say that the sum of the probabilities has to be equal to 1. The particle has to be somewhere, and it's the same thing in cases like this. That's when we talk about a normalized probability. So more succinctly, we can simply write that the mean of the function then can be written as the probability of obtaining u times that function. And there are some other useful properties of this as well. F of u plus g of u. So I have two functions. The mean of those two functions is equal to the sum of the means of those functions. That's kind of nice. And similarly, if c is some constant times f of u, the mean value of that is going to be equal to c times the mean of f of u for any constant c. It would be nice if we could verify some of this in conjunction with the random walk problem. So in that case, we found that the probability of taking n1 steps to the right was equal to n factorial over n1 factorial, n minus n1 factorial, p to the n1, q to the n minus n1. First, let's verify that this distribution is normalized. Now, we know that it has to be, because he can either make one step to the left or one to the right. He's making one or the other. Nonetheless, we know that if we sum this from 0 to n, the sum is going to be p plus q to the n by the binomial theorem. And of course, the probabilities themselves, in this case, are 1/2 plus 1/2, so that gives me 1 to the n, which of course is 1. So the probability distribution is normalized. Let's take it a step further and calculate the mean number of steps to the right that the student would take. So the mean number of steps, n1 bar, I could write as n1 equals 0 to capital N, p of n1 times n1. And I could write that as sum n1 equals 0 to n factorial, n1 factorial, n minus n1, n minus n1 factorial, p to the n1, q to the n minus n1 times n1. Well, this reminds us a lot of the binomial expression, except for this factor of n, which presents a bit of a problem. But there's a trick we can do. Watch. I can express n1 times p to the n1 as p times the derivative with respect to p of p to the n1. And if I do that, I can rewrite this sum n1 is equal to sum n1 equals 0 to n, n factorial over n1 factorial, n minus n1 factorial, p dp, p to the n1, q to the n minus n1. Notice what I get. In this case, I can pull a p out and I get p times ddp of p plus q to the n is equal to pn p plus q to the n minus 1. Isn't that cute? Which tells me that n1 bar is just p times n, because this is just going to be equal to 1. That's a nice little trick to show what the mean value of n1 is. Of course, same deal for n2, or for n minus n1 is going to be equal to q times n by the same argument. And of course, if I add the two means together, n1 mean plus n2 mean, I will get p plus q times n. This is going to be 1. And of course, it's just n as we would expect. Very nice. So this is a very nice way of dealing with two-state problems, sometimes. Let's suppose, though, that we're talking about not 10 heads or 12 coins or 20 coins. Suppose we're talking about something like 500 coins. Well, you can imagine looking at these expressions, your calculator isn't going to be too excited about doing 500 factorial or 1,000 factorial. And so it might become a little bit cumbersome to use the binomial distribution when you have extremely large numbers. We have a way, though, of dealing with those large numbers. And that way is called the Gaussian distribution. We will right now derive the Gaussian distribution because it will save us when we have numbers that are much too large to be putting as factorials into our calculator. I'm going to motivate it this way. Suppose I have really, really large n, really, really large. I know that the binomial distribution will yield a very pronounced maximum in probability for some value. Let's call it n1 equal to n1m for maximum. So I expect to see a probability distribution that may be relatively small, except sharply peaked at a point. Also, I know that this probability will decrease precipitously when I move away from n1 equal to m1 and n1m in either direction. So what I'm going to do is I'm going to treat p, the probability of n1, as a continuous variable, or a continuous function. And I'm going to employ differential calculus to find out which value of n1m maximizes the probability distribution. So what I'm going to do is I'm going to set the log of p with respect to n1 for n1 equal to n1m equal to 0. Okay? Treating it as a continuous function. Now, let's do this. I'm going to write n1 as n1m plus a. And I'm going to expand the log of p in a Taylor series about n1 equal to n1m. So we'll write the log of p n1 is equal to the log of p of n1m plus a1 times a plus 1/2 a2 times a squared plus all the way up the line where I'm going to use a, let's call the a's, a sub I, will be equal to the ith derivative of the log of p with respect to n1 I. Okay? So each of these terms represents a logarithmic derivative as I go up the chain. Of course, each one gets progressively smaller and smaller. Now, next point. Since we're expanding about a maximum, it has to be that a1 is 0. Why? Because the first derivative of the function at a maximum is always equal to 0. So to a good first approximation, I can write the probability as P sub m e to the minus 1/2 absolute A2 A squared by anti-log, right? Interesting, interesting. So what I can say then, let's look at this expansion in a little bit more detail. So I can write the log of P of n1 as the log of n factorial. Take the binomial. So log of n1, log of n, minus the log of n1 factorial, minus the log of n minus n1 factorial, plus n1 log of p, plus capital N minus n1 log of q. So take the binomial expression, and I've taken the log of the whole kit and caboodle, right? And that's what I get. Okay, this looks horrible. So I'm going to have to make some approximations. First of all, I can say d log n factorial with respect to n is approximately just the log of n. That's fair enough. Certainly the 1 in there doesn't make a difference. So I can say d log p with respect to n1 is equal to minus the log of n1 plus the log of n minus n1 plus the log of p minus the log of q. Now, since the above first derivative is 0, I guess I have to go back to this board. I can say the following. Log of n minus n1m over n1m times p over q is equal to 0. Or n minus n1m over n1m times p over q must be equal to 1 since the log is 0. And therefore, n1m is equal to np, since p plus q is equal to 1. Now let's take the second derivative. Second derivative of the log of the probability with respect to n1 is equal to minus 1 over n1 minus 1 over n minus n1. If I evaluate for n equal to, I should say for n1 equal to n1m, I get a2 is equal to second derivative log p with respect to n1 is equal to minus 1 over n1 minus 1 over n minus n1. Which I can write then as 1 over n, 1 over p, minus 1 over q, or minus 1 over n p q. Now we can determine the normal p sub m by normalization condition, and what I'm going to do is say p of n1 dn1 integrated over all space is equal to 1. I'll write that as p sub m, integral over all space, e to the minus 1/2 a dA. 1. The value of this integral is 2 pi over the absolute value of a2. Therefore, I can write my probability is equal to square root a2 over 2 pi e to the minus 1/2 a2 n1 minus n1m squared. Or, since a2 is equal to minus 1 over n pq, I can write this as p of n1 is equal to 1 over 2 pi times npq to the 1/2 e to the minus n1 minus np quantity squared over 2n3q. And this is what we call the Gaussian distribution. So for example, suppose I said the following, suppose I toss 500 coins, I can calculate the probability that 256 heads will result from those 500 coins by plugging in the following. I'll put in 500 here. P and Q are both 1/2. N1 we want to be 256. If I multiply all that out, notice I don't have these really wonky factorials to put into my calculator. Multiply all this out, immediately I get a nice answer, and it turns out to be 0.30, I should say 0.0308. So there's a 3% probability that if we flip 500 coins, 250